So in our last lecture, we talked about warp drive, basically the Alcubierre drive, the ability to stretch and squeeze space on demand. The problem is it would take so much energy, you would basically have to convert the entire galaxy into energy, all the matter in the galaxy, E equals mc squared, take the entire galaxy, convert it into energy in order to move just a tiny little thing, the size of probably the size of a cell phone, at close to the speed of light. So it or beyond the speed of light. So it would not be a realistic sort of thing. So the other thing we talked about were cosmic strings. And I said, if you freeze something, things often don't work. So here we have a semiconductor that was laid down, and it was laid down in a nice little pattern, but the pattern was also forming from another direction, and when they met, they didn't match. So this is a topological defect. So that would actually affect the semiconductor device. You could build a device or a chip on one side, or the other side, but you could not build a chip that overlapped those two parts there. You can see the same thing again. If you freeze something, then if the water starts freezing on one side of an ice cube and then freezing the other side of the ice cube where it meets in the middle, the molecules don't line up just right. And so it looks like a little crack in there. The universe, if this is what happened, if you freeze out the strong force, it's possible that running through the universe are these cosmic strings. The cosmic string would be like cracks in the universe. Now, physically, what it would be like, it'd be like a very, very long singularity. It would interfere with gravitational forces and stretching of space. It would tend to pull things towards it, like gravity. In fact, it would probably be causing superclusters to line up along them. Superclusters avoiding, therefore, the spaces between the strings. So this would be one way of getting walls and voids. That got to have a Star Trek reference once in a while. This is probably going to have the last chance I get to make a Star Trek reference. But in Star Trek Next Generation, the Enterprise actually kind of ran into a cosmic string fragment. So, which caused all kind of mess on the Enterprise. But all right. Shortly after all this stuff was happening, inflation, we had the Quark Epoch. At this point, what happens is that you're creating particles for the first time, real particles, gravity starting to have something to act on, you're making matter and antimatter, you leave a little bit more matter behind, you're starting to create a few electrons and positrons, and so you have free quarks. Towards the end of this period is when you start ending the Quark Epoch, and the quarks start being confined into what we call baryons. So they start becoming confined into protons and neutrons, or sorry, not baryons, but hadrons. So the hadrons are made up of the quarks, and so the hadrons and leptons start forming here. Hadron Epoch, you start confining the quarks. Now you get protons, and you get neutrons, and eventually you start getting stable electrons and positrons. And at that point, for the first few minutes of the universe, about the first 3 or 4 minutes of the universe, you start fusing all kind of stuff, because now you start making protons. They start running into each other, and they start to make deuterium. Deuterium fuses, makes helium. You have so many things in here. You throw an extra proton in there now and then, and you can start making a little bit of lithium. And so for about the first 15 minutes of the universe, you're making stuff, and especially in the first 3 minutes. But after that, you start making fewer things. By about 15 minutes, the universe has made everything. It's now expanded so much, cooled off enough, things are so far apart, you're not making new things. Okay, so nucleosynthesis. During this period of time, you make a lot of hydrogen, and in fact, you can calculate about 9 out of 10 atoms are hydrogen atoms. you're going to make a little bit of helium, about 1 in 10 atoms are helium atoms. And everything else is going to be like way less than that. Now, exactly how much deuterium versus hydrogen or any kind of lithium make in there depends exactly on the density and flatness of the universe. And so what we discover is that most of the stuff in the universe was formed here. In fact, just about all the hydrogen atoms and helium atoms and everything else you find in the universe like that, hydrogen and helium, were formed in the Big Bang. Some helium is formed in stars through nuclear fusion. Okay. But theoretically, almost all the hydrogen that you find in the universe goes back to the Big Bang. You can actually, again, work out the proportions of everything, how much is what in the universe, and what temperature that would have to be, and figure out where it all matches. And again, that would tell you the temperature of the universe at the point that all this stopped, and that would be highly dependent on the density of the universe. This is another way of calculating the Hubble constant, and also the density of the universe. Once again, the Hubble constant, come up figuring it this way as opposed to looking at the stuff in the universe, is a little bit lower. And once again, you do this and you come up with a flat universe. Well, as eventually everything kind of came together, you had recombination, light started shining, universe was so hot that the particles were giving off a little bit of light, kind of a dull red color, so the entire universe would be reddish. But as the universe expands, that red color stretches through the red shifting into infrared. So the entire universe is infrared, but you don't really have hardly any visual light. You don't have stars yet. The stars have to come together in order to produce, the sort of pressure to make heat to make visible light again, and that's not happening. And so the universe is pretty much dark. We call this the dark. Eventually, you start making the first stars. The very first stars are expected about 200 million years after the universe formed. Actually, they expected them about 400 million years after the universe began, but they have found some evidence that some of them started forming at 200 million years earlier. These population 3 stars, they have nothing but hydrogen and helium in them. That's because that's all that was there. Even population 2 stars have a teeny tiny bit of extra stuff, just not much, but these had none. The universe was so warm, you had to have even more mass in order for them to pull together. And so there were probably hundreds of solar masses in size, much bigger than anything can be made now. Super hot, blue and ultraviolet temperatures, but that's redshifted into the infrared now. The Spitzer infrared telescope, it's a space-based telescope, took pictures of the background radiation in infrared, and you see clumps of bright spots of where these first stars were starting to light. So that begins what we call the Stelliferous era. The Stelliferous era began about the time that the first stars started to form, and some of them, of course, being supermassive stars, died super violently, and so as hypernovae. And so, in fact, the gamma ray burst that was discovered in 2009, very, very distant gamma ray burst, was found to be about 13 billion light years away. That makes the universe way younger than they originally had expected stars to have formed. So that may have been one of the very first stars to have ever formed. Well, eventually what happens is that all these things clump together. You get the stars and the gases clump together to make the little blobs that then come together to make galaxies. And